once we know how to take the derivatives of the hyperbolic functions, we can use implicit differentiation to find the derivatives of their inverse functions. Let's say y is the inverse sine, or the arc sine, you could call it. That would mean that the sine of y is x, and if we take the derivative of both sides with respect to x, the derivative of the outside here is the cosine, evaluated the inside times the derivative of the inside. Over on this side, the derivative of x with respect to x is just 1. So dy dx is equal to 1 over the cosine of y. But we don't know what the cosine of y is. However, we do know what the sine of y is. So we know that the sine of y is x. We also have this identity that the cosine squared of y minus the sine squared of y is equal to 1. So that tells us that the cosine squared of y is equal to 1 plus the sine squared of y. And we know the sine of y is x, so this is 1 plus x squared. Now, if you look at the definition of the cosine of y is e to the x plus e to the negative x all over 2. Well, e to the x is positive, and e to the negative x is positive, and the sum of two positive numbers is positive, and a positive divided by a positive is positive. That's greater than 0. So if I know that the cosine squared of y is 1 plus x squared, then the cosine of y could be either plus or minus this square root, but since I know the cosine is positive, I've got to use the plus sign. So the cosine of y is the square root of 1 plus x squared. That tells us that dy dx, which means the derivative with respect to x of the arcsine, since y is the arcsine, is equal to 1 over cos y, and cos y is the square root of 1 plus x squared. So the derivative of the arcsine is 1 over the square root of 1 plus x squared. Compare that to the derivative of the arcsine, so the elliptic sine function. That's 1 over the square root of 1 minus x squared. So similar, just a slight difference there. Let's do another one. Suppose we want to find the derivative of the arc cosine. Now, cosine is a function that's always positive. In fact, if you think about this graph, as x gets larger and larger, this term fades away. So basically, when x is 0, we have e to the 0 plus e to the 0, which would be 1 plus 1 is 2. 2 over 2 is 1. So this function starts at 1. And as x goes forward, it grows exponentially. Right? In the long run, this term fades away, and you basically have 1/2 e to the x. On the other hand, as x goes backwards, e to more and more negative numbers disappear, but the opposite of negative is positive, so these numbers get bigger and bigger, so you get exponential growth this way. So this function doesn't really have an inverse unless you cut it off. So the typical thing is to cut off the left-hand branch. Now you have an inverse. So that means to have an inverse, then x has to be greater than 0. So suppose y is the arc cosh of some number. So we're thinking that we have some value here and we undo the cosine to get back this number. That would mean that the cosine of y is equal to x. Okay, let's take the derivative of both sides with respect to x. The derivative of the cosine is the sine. Alright, so we take the derivative of the outside, evaluate the inside, times the derivative of the inside. That's just the chain rule. And the derivative of x with respect to x is 1. So dy dx is equal to 1 over the sine of y. But we know that cosine squared minus sine squared is equal to 1. So therefore the sine squared of y, if I move that over and bring this 1 over, is equal to the cosine squared of y minus 1. So the sine of y is equal to the square root of the cosine squared of y minus 1, well, technically the plus or minus square root of the quotient squared of y minus 1. But since we know that if we're going to do this, that the y value, the inverse function's got to be over here, we know that y is actually positive, and if y is positive, the sign is positive, so we know that it needs to be the plus sign. So the sign of y is the square root of the quotient squared of y minus 1, but the quotient of y is x, so that's the square root of x squared minus 1. So we just figured out that dy dx is 1 over, that would be the derivative with respect to x of y, which was the cosine inverse of x. And we figured out that dy dx is 1 over the sign, so that's 1 over the square root of x squared minus 1. So compare that to the derivative with respect to x of the arcsine of x. We got 1 over the square root of x squared plus 1. Let's do another one. What if we need to find the derivative of the arctan? So let's let y be the arctan of some number x. That would mean that tangent of y is equal to x. So if we take the derivative, we get that the derivative of the tangent is the secant squared. So the secant squared of y times dy dx is equal to 1. So dy dx is equal to 1 over secant squared of y. However, because cosine squared y minus sine squared y is equal to 1, if we divide both sides by cosine squared, we find 1 minus the tangent squared of y is equal to 1 over the cosine squared, which would be the secant squared of y. So, and we know that the tangent of y is x, so 1 minus x squared is equal to the secant squared of y. So that tells us that the derivative of y with respect to x, which is the derivative, since y is the arctangent, this is arctangent, this is the derivative with respect to x of the arctangent of x. We figured out that that's 1 over the secant squared, but the secant squared is 1 minus x squared, so we get 1 over 1 minus x squared. So just compare that to what happened in the elliptic case. In the elliptic case, the derivative of the arctangent was 1 over 1 plus x squared. So this is kind of this function has a slight difference from the arctangent when you have the arctangent. It's similar. So far we've seen that the derivative of the arcsine is 1 over the square root of 1 plus x squared. The derivative of the arccosine is 1 over the square root of x squared minus 1. And the derivative of the arctangent is 1 over 1 minus x squared. Now these restrictions here, that x is greater than 1, if you look at the graph of the cosine, it's always greater than 1, and so this is a natural restriction on the inputs. The graph of the tangent is always between negative 1 and 1, and so that's why this restriction comes up. If you follow a similar pattern, then you can see that the derivatives of the remaining 6 hyperbolics are these values. So you might try and see if you could actually produce those results by working with those, kind of following what we did in these cases.